Okay, welcome back. We are discussing energy analysis for closed system. So this is a part 4 of the module. So in this particular lecture we will be covering specific heat at constant volume and constant pressure, and then we will try to relate this specific heat to the changes in the internal energy and enthalpy, and specifically for ideal gases. So what is a specific heat? Okay, so let's take an example from our daily life. Based on our experience, we know that it takes a different amount of energy to raise a similar amount of temperature for two different objects. So just take an example of, let's say, iron and water. So it takes around 4.5 kilojoules to raise temperature of iron from 20 degree to 30 degrees Celsius. Okay, for 1 kg of iron, the same mass, that is 1 kg, if we consider for water, the amount of energy to change from 20 degree to 30 degrees Celsius is 41.8 kilojoules, which is quite low for the case of iron, which requires only 4.5 kilojoules to raise 10 degree Celsius for same amount of mass. Okay, so it clearly, you have same mass and same change in temperature, but it requires different energy. So there is a different capacity to store energy, and this capacity is reflected in thermodynamic property, which we call it a specific heat. So to compare energy stored capability of various substance, we define a term called specific heat, which is a property which is defined as the energy required to raise the temperature of a unit mass of a substance by 1 degree. Okay, so this is the illustration. So for example, you have 1 kg of this particular substance. It requires let's say 5 kilojoules to raise 1 degree Celsius. Thus its specific heat is 5 kilojoules per kg degree Celsius. You can also write it in this form, Kelvin, because delta T for Celsius is same as delta T in Kelvin. Now there are two specific heats depending on how the process is. One is called specific heat at constant volume, and other is called as specific heat at constant pressure. Okay, so the way we define is CV. So that is a specific heat at constant volume, which is the energy required to raise the temperature of a unit mass of a substance by 1 degree, keeping the volume constant. And similarly, for the case of specific heat at constant pressure, is the energy required to raise the temperature of a unit mass by 1 degree, keeping the pressure constant. So this is by definition, and it is universal. It doesn't depend on particularly which substance you're talking about. Cp is always greater than Cv to accommodate energy needed for expansion work. So for example, in the case of a helium, okay, you have a volume which is constant here, mass is 1 kg, and the delta T, again we are keeping it 1 degree Celsius, because that's a change. It requires 3.12 kilojoules to raise 1 degree, and that's why Cv is 3.12 kilojoules per kg degree Celsius. On the other hand, when you consider movable piston here, which means the volume can change, you need more energy, okay, in order to accommodate expansion work, and thus more energy for changing the temperature by 1 degree Celsius, and thus your Cp is higher than Cv. Okay, so that's a typical behavior of a Cp and a Cv. Okay, so Cp is usually greater than Cv. So let's now try to connect this Cp and Cv in terms of thermodynamic parameters. So we can consider a fixed mass, okay, in a stationary closed system undergoing a constant volume process. Okay, so which means there is no boundary work. So you can come up with the energy balance. So this is your energy balance. Now this is nothing but the net energy transferred to the system. Okay, so this is the net energy transfer to the system. So if we assuming the Cv, which is defining is the energy required to raise 1 degree, thus we can say that this by definition is going to be Cv times the change in energy, or in terms of differential form is a dt, and this is by definition we are saying this to be equal to du. So this is at constant volume. Thus if you consider in the differential form, this would be Cv is partial differentiation of u with respect to T at constant volume. Using similar analysis for a constant pressure, okay, where you are doing expansion and compression at constant pressure, the expression for specific heat would be Cp, and that will be related to your enthalpy, change in enthalpy with respect to the temperature at a constant pressure. So the definition of Cv would be the change in internal energy with temperature at constant volume. Okay, it's a partial derivative of internal energy with respect to temperature, and for the case of Cp is a change in enthalpy with temperature at constant pressure. Okay, so what about these equations which we have written, the expression of Cp and Cv, are they valid only for specific substance? The answer is no. These equations are valid for any substance undergoing any process. Okay. Now you also notice that Cp and Cv are related to changes in the U and changes in the enthalpy, which essentially means they are related to the properties, and hence they are also itself properties. So specific heat, as I said, is expressed in terms of other properties, hence they are property themselves, which essentially means you can define specific heat in terms of intensive variable temperature and pressure. So that is, energy required to raise the temperature of a substance by 1 degree is different at different temperature and pressure. So they are variable, as you already mentioned that they depend on intensive variable as they are just a property, hence they will also vary with temperature and pressure. With an example is for air. So for the case of air with a mass of 1 kg, a change from 300 to 301 Kelvin, just 1 Kelvin change, the energy required is 0.718 kilojoules. On the other hand, at a very high temperature, a change from 1000 to 1001 Kelvin, the energy required is much higher. So that means it depends on the temperature and pressure. Just to remind, Cv is related to the variation in the internal energy, Cp is related to the variation in enthalpy. Okay. Now what are the units? The units are, as I said, is Celsius. Units are kilojoules per kg per degree Celsius or kilojoules per kg per Kelvin. Okay, are they same? The answer is yes, they are identical. The reason is that delta T for degree Celsius is same as delta T for Kelvin. Okay, so now let us consider the case of ideal gas. So we know that ideal gas, we can write PV is equal to RT, where R is a gas constant. Now what about the internal energy for such a system? So the idea is basically to come up with an expression of Cv and Cp. The internal energy apparently was shown by Joule that it depends on only temperature for the case of ideal gas. What he did is he took two tanks, one with high pressure air, which is this, okay, and he connected with another tank which was evacuated at a zero pressure, connected with the pipe and with a valve. He put these two tanks in a water bath at a certain temperature, allowed it to thermal equilibrate, and once the thermal equilibration was attained, he opened the valve to let the air pass from one tank to another until the pressure equalized. Now Joule observed that there was no change in the temperature, so that means the delta T here, it was 0, and he assumed that no heat was transferred from the air or to the air. Since there was no work done due to the expansion against zero pressure, or it was a free expansion, he concluded that the internal energy of the air did not change. So, and thus he concluded that in order to change internal energy of an ideal gas, you need to change your temperature. Thus, it depends only on the temperature. Okay. So that was the classic experiment which he conducted in 1843 and concluded this property of ideal gas, where U is depends only on temperature. Now we can take a definition of enthalpy, okay, and also prove that if U depends on T for the case of ideal gas, H also depends on T. So this is your definition of enthalpy, where H is equal to U plus PV, and now you can make use of ideal gas equation of state, which is PV is equal to RT, plug in there. So what you get is H is equal to U plus RT. Now given that U for ideal gas just depends on temperature, and thus H also depends on temperature. Okay, so enthalpy depends only on the temperature. Joule also showed that there is a deviation from this particular expression for the case of gases which deviates from ideality. So for the non-ideal gases, these expressions do not hold. Okay. Now if this is known that U and H depends on temperature, then you can take the definition of Cv. This is represented in terms of partial derivative of internal energy with respect to temperature. So given that u is only function of temperature, you can change from partial differentiation to ordinary differentiation, which is this, okay, and thus you can write du as simply Cv T multiplied by dt, okay. Similarly, you can also do the same exercise and you can write dH is equal to Cp multiplied by dt. So this is for ideal gas. Okay, so now given that expression, you can easily integrate. So this would be your change in internal energy for ideal gas. Ideal gas during a process from state 1 to state 2, okay. So this is going to be your expression for delta U, okay, and this would be the expression for delta H. So you are just integrating nothing but dH is equal to Cp dt, and thus your delta H is nothing but Cp delta T. Okay, so this will be the change of the internal energy and enthalpy for ideal gas. Now in order to obtain the change, we need some relation of Cv and Cp as a function of temperature, because these are given here. So now that's the important aspect in order to come up with the values. Now let's look at it, what happens for the specific heats of real gases, and particularly at low pressure. So at low pressure, all real gases approaches ideal behavior, that we know that. Now at low pressure, your gases turn out to be at low density, or in a sense they are very far from each other, and hence they do not experience each other's presence. So they don't get influenced, and due to that their behavior can be approximated as an ideal gas behavior, and thus we are going to make use of low pressure approximation for the gases. We can make use of the specific heat values for the gases. So just take a look at the real gas behavior at low pressure. So as I said, all real gases at low pressure approach ideal gas behavior, and therefore once they do that, their specific heat depends only on the temperature, as we have already mentioned that ideal gas specific heat depends only on the temperature. So specific heat for real gases at low pressure are given in this particular temperature, where we have plotted specific heat of real gases at zero pressure, and this particular values represent 0. Again, this is Cp, which means it's a zero pressure, a constant pressure, but extremely low value. That's why it is Cp, and the bar represent that it is molar basis. So this is your typical specific heat for real gases. This is the monoatomic gases. These are diatomic, and these are the molecules, and you can clearly see that for monoatomic the specific heat at low pressure is almost constant for all the temperatures. On the other hand, this is almost linear nature, and this has curvature, but we can see that this is almost linear at small range of temperatures, okay. So we can approximate different ranges, and we can consider this to be a linear within that. So this particular plots or the behavior can be fitted to some analytical expressions. For example, you can put you can fit this expression into a cubic form or third order polynomials, and this is something which we are going to make use of it, because at the end we have to make use it in order to find out changes in the internal energy or enthalpy. Let's take a look what are the different ways to make use of specific heats. Okay, so this is one way to represent specific heats. Now specific heat, as I said, you can fit these variations as a function of temperature by this third order polynomial. Okay, so and then these are tabulated in table A2 for a certain substance. Now I haven't given the complete list of substances, so you can look at table A2 for the complete list. These are the values A, B, C, D, and this is the temperature range where this particular approximation of fit to the real data is valid within certain error. Okay, so average is around 0.34%, which is really not bad, very good in fact. So the use of ideal gas specific heat data, okay, as an approximation is limited only to low pressure. So you cannot make use of it at high pressure, okay, remember that. But you can still make use of it at moderate pressures. Of course, you can ask like what is the range for moderate pressure, but this depends on different gases. Okay, so what we are going to use in this particular course will be approximation for at low pressures. Okay, so as long as the gases do not deviate from ideal gas behavior, we can make use of this approximation. Okay, so since we have to integrate in order to find out the changes in the internal energy or enthalpy, if we can make use of this third order polynomial, it is going to be time consuming. So because you have to integrate the series and then you have to put the values. So what we have done, it has been done that the values of U and H data for a number of gases have been tabulated. These tables are obtained by choosing an arbitrary reference point. So because you have to provide a reference point 1, and then if you, let's say, keep it a reference point where you can assume that the Cp for that value is close to 0, then whatever the values would be U and H for a specific temperature. Okay. So in this case, table A17 is given to you, in which 0 Kelvin is chosen as a reference temperature. Okay. So that's another way. So instead of integrating and making use of table A2 for a specific temperature, you can directly make use of table A17. So that's another way of calculating the change. Now the other possibility we can do is, for the case of a small temperature intervals, you can approximate also. So you can consider the variations linear. Okay, so I was mentioning in that in this particular plot that this particular range, though there is a change in curvature, though there is a variation which is significant, but for a small range you can always consider to be linear. So you can linearly approximate. Okay, so that's something which we can consider in this. Another possibility is to obtain the change or to obtain the values of Cv or Cp. So this is an example here. So you have T1 and T2, and what you can do is you can take the Cv for the complete process. The process is occurring from 1 to 2, but you can consider Cp average or the average of specific heat at T average values. So and then you can directly use this as a constant and integrate only the dt part. So in this case, U is Cv dt. Okay. So that gives you this thing. So this is another way, or this is useful only for small temperature range. Delta U equal to Cv delta T. This relation is valid for any kind of process. It need not be constant volume. This expression requires that we use specific heat at constant volume, but this expression is true for whether the process is occurring at constant volume or process is occurring at constant pressure. Okay, so for example, in this case, you take the volume is constant. Okay, the temperatures are changing from T1 to T2 by providing some heat. The delta U in this case can be directly using Cv delta T. Okay. On the other hand, this is another example. Here delta U can also be calculated by using the same expression. Okay, though P is constant. So similar argument can be given for Cp. Okay, so these expressions are true irrespective of the process. Okay, so let's summarize the different methods to obtain changes in the internal energy and enthalpy. So as we discussed, there are three possible ways. So let's try to summarize. One is directly use the tables. Okay, which essentially is going to be much easier. Okay, it's one of the most accurate way. The other is you take the expression of Cv, okay, as a function of temperature, as we where the polynomial functions are used, and then you integrate it. It's time consuming, sometimes cumbersome, but it's still very accurate. Okay, so this is another way. Okay, and the third is, of course, you consider an average Cv for a specific temperature range, and then you take that average and just multiply by delta T. Now this is accurate only, or reasonable accurate only, when the delta T or the range of temperature which you are considering is not very large. So these are the three different ways we are going to make use of it in this particular course. So that will be the end of this lecture. So in the next lecture we are going to talk about specific heat for incompressible substances, and we will consider a couple of examples before concluding this particular module. Okay, see you in the next lecture.